Okay. Right, could you please confirm if you can see the slides on the screen? Okay, thank you. Great. So today we're going to move on to our next topic, which is intrinsic and extrinsic semiconductors. So we've covered for me energy and density of states till yesterday. So we're going to do a few recaps before we move on into this new topic, okay? So let's just go through this page as what we've done with the previous lectures as well, right? On challenge what you have learned. So let's go to question number 1 before we move on to the new topic. What is Fermi Dirac distribution function? Anyone? Let's recap. You can unmute yourself. You can also write down in the chat box. What do you understand so far by the Fermi Dirac distribution function? Anyone? First question in the morning for the morning class. Any volunteers? Let's warm up a bit. What is Fermi Dirac distribution function?
The property single states where
Siapa yang tak biasa ni dengan dengar suara lagi? Cell 1? Cell 1? Any answer on this? Cell 1?
Can you hear me, doctor?
I can. Okay, yep, Ziki. Go ahead.
It's the probability.
I can hear you, but very slow.
So
Can you be louder a bit, Zuki?
it's the probability of a single energy state where electrons are occupied at a given temperature.
Okay, all right. It's the probability of finding electron at that particular energy and that specific temperature. Okay. So how about the equation? Can you recall the equation?
It is a function of E equals to 1 over 1 plus exponential over E minus EF over KT.
Okay, all right. So that's the equation. So Fe 1 over 1 plus exponential component of E minus EF over KT, okay? So good, that's done. So let's move on to question number 2. What is density of states? Or DOS, as we discussed. What is density of states? How about Zulaika? Zulaika? Okay, I got something here. From Zul. Right, number of allowed energy states per centimeter cube of energy interval. Okay, so that is the density of states. Number of allowed energy states per centimeter cube of energy interval. Or the analogy that I explained to you yesterday for you to understand is like the size of a room that can fit a certain number of people, right? It's how many people can you push or how many can you squeeze into a room. So it's the size of that room that can accommodate certain number of people. So it's just like the number of allowed energy states per centimeter cube of energy interval. So that's DOS. Right, what is then probability of occupation? What is number 3? Probability of occupation. So that's the keyword there. Anyone? Probability that an allowed energy state is occupied by an electron. Okay, good, Shasha. And that's given by which equation, Shasha? This probability of occupation. Which equation governs this probability of occupation? Right, Fermi-Dirac distribution function. So Fermi-Dirac, so it's Fermi-Dirac distribution function, right? So it's given by the very same equation. And finally, how do we calculate density of free electrons? Okay, what is the simple equation that we learned yesterday in order to calculate the density of free electrons? Anyone? Density of free electrons or free electron density.
Is the product between the probability that Fermi-Dirac distribution function and the number of allowed the density of states.
Okay, right? So it's NE equals to FE okay, Salwan, all right, no worries. So it's a Fermi-Dirac distribution function, or you can also say probability of occupation times DOS, right? DOS. Okay, go back to the equation. Okay. So on the other hand, if you got a question on how do you calculate density of free holes, how do you distinguish the equation?
Just 1 minus the full equation.
1 minus, right? Okay. So this DOS is NCE for free electrons. So if you have to calculate for holes, then it's 1 minus FE, right? 1 minus FE. Then what about this? What about the density of states?
Change to density NC over the H.
NVE, right?
NVE, yeah, NVE.
Right, NVE, density of states of hole in the valence band. Okay, so that's the difference between electrons, electrons and hole. Okay, electrons is Ne, hole is Pe, and your probability for electron is Fe, whereas the hole is 1 minus Fe, and density of states for electron is NCE, C subscript, and the hole is NVE, V subscript, right? So that's the thing. So we learn now that you can calculate the density of free electrons and free holes by first understanding the probability of occupation, or given by Fermi-Dirac distribution function, times the concept of density of states, which you have to calculate beforehand, right? So in this topic, we're going to learn about intrinsic and extrinsic semiconductors. And we have discussed very, very briefly about the concept of intrinsic and extrinsic semiconductors. So in this topic, we're going to look into more details of both, right? So we're gonna look at intrinsic carrier concentration, whereby we've discussed before that intrinsic means pure. So when we say it is an intrinsic semiconductor, that simply means it is a pure semiconductor, and it is not doped by any impurities or any dopants in order to alter its conductivity. Whereas if you talk about extrinsic carrier concentration, you're talking about extrinsic semiconductor, where the semiconductor is doped by dopants or impurities, intended impurities, because it's also called dopants, right? Intended impurities. We'll learn about doped silicon, which is essentially extrinsic semiconductor. So we're going to look at Fermi level in doped semiconductors. We'll discuss this briefly, and you will find out later that you're going to see some difference between the Fermi level in doped semiconductors versus in undoped semiconductors. So we've also discussed this briefly, where we've learned that in undoped or in intrinsic or in pure semiconductors, the Fermi level stays right in the middle of the band gap, or equals to Eg over 2. Okay. Or if you talk about crystalline silicon with 1.12 electron volts, so that means your Fermi level stays at about 0.56 eV, right? So we're going to learn at the concept of law of mass action, conservation of charge, and then degenerate semiconductors, where you're going to see that when you heavily dope a semiconductor, it's going to turn into a degenerate semiconductor. So we're going to see at what level is going to turn into a degenerate semiconductor. Okay. What is then compensated semiconductors? So some semiconductor can be compensated in some condition. And then finally, variation of EF with doping and temperature. Okay, so you can actually alter your EF, level of EF, with doping and with temperature variation. Okay. So let's get started with intrinsic. As previously discussed, intrinsic semiconductor is a pure semiconductor. Okay, so you can either say it's intrinsic, which means pure, or it also means undoped. Okay, undoped semiconductors. So that means you don't, if you assume your host atom is silicon, so that means you only have pure silicon to play with. So you don't have phosphorus incorporated, or antimony incorporated, or aluminium or gallium in order to alter the conductivity. So it's just the pure silicon itself, right? So that is meant by intrinsic semiconductor. So if you look at the intrinsic semiconductor details, it can be defined as a pure semiconductor or without dopants, as we discussed. So there's no dopant incorporated into the lattice. And in an intrinsic semiconductor, the number of charge carriers is determined by the properties of the material itself. Okay, so the properties of the charge carriers is determined by the properties of the material itself instead of the number of impurities incorporated, because there is no impurities in the lattice to begin with. So whatever you have is what you have in terms of its electrical properties. In intrinsic semiconductors, the number of excited electrons and number of holes are equal. Okay, in intrinsic, number of excited electrons and number of holes are equal, or you can represent this by an I, intrinsic density of carriers in intrinsic semiconductors equal to number of electrons and also equal to the number of holes. Okay, so I have a question here. Why the number of electrons and the number of holes are equal? Any ideas? Why the number of electrons and the number of holes are equal? Any opinion on this? Anyone? Kenapa kita ada the same number of electrons and holes in this case? Okay. Students waiting for me. I don't get any. Let me see. I don't get any notification. Usually I get some notification when students would like to enter. Let me see. Okay, I just got it here now. Few students. Okay, sorry for that. Okay. So thanks for informing me as well. Thank you.
Doctor, is it because the electrons are still bounded in the energy level? Means that they are not being free.
So in this case, it is number of excited electrons. So the number of excited electrons are equal to number of holes as the free carriers available. Okay, so any other opinions? Why number of excited electrons are equal to the number of holes? Before we discuss, just would like to get your opinion on this.
Hi, doctor. Can you hear me?
Yes, yes,
I
Patient,
think
yes.
I think at the excited state, the electron will jump to conduction band, and then it create a same number of holes.
Yes, right, good. So when the electrons are excited, it's actually leaving the same, it's actually leaving for every pair of electron and hole. So you're going to get free electron with a free hole at the same time, okay? So when your electrons are excited into conduction band, it's going to leave a free hole in the valence band at the same time. And before that, to be able to generate a free electron hole pair, you need to break a bond. Okay, you need to break a bond. You need to break a bond. Break a bond, then only you're gonna get free electron hole pairs. Electron, I just write here as EH pairs, yeah, electron hole pairs. So by breaking a bond, you're gonna get a free electron hole pair. So one pair created by breaking a bond. So that means whenever you have a thermally excited electrons, you're going to have the very same number of holes at the same time. 1, 1, 2, 2, so on and so forth. And therefore, in an extrinsic, extrinsic will be different. It's about the dope. You already have foreign impurities incorporated by your own design, by your own control. You can actually design or customize or tailor the level of doping for whatever application they want. But in an intrinsic, the pure material, the number of electrons, the number of excited electrons are always equal to the number of holes because you need to break a bond for them to be created in the first place. And therefore, Ni is equal to N naught and is equal to P naught. This is very important in intrinsic semiconductor because this is going to be different when you talk about extrinsic semiconductors. Okay, so you have to bear that in mind. Ni equals to N naught equals to P naught. And Ni here means the carrier density of free electron in intrinsic, I for intrinsic, and naught here mean thermal equilibrium condition. Right? N naught density of electrons at thermal equilibrium condition in intrinsic semiconductors equals to density of free holes at thermal equilibrium in intrinsic semiconductors. So Ni equals to N naught equals to P naught. So the intrinsic carrier concentration is a very strong function of temperature. So it's going to change at different temperatures. So we have learned about, if you can recall, we have learned in the past few classes and also yesterday, if you can recall this, Fe against E, or you can plot E on the y-axis, Fe on the x, and you're going to see this T equals to 0, T equals to T1, T equals to T2, and you're going to see electrons, thermally excited electrons are jumping or are getting excited into the conduction band, leaving free holes in the valence band, right? So it is strong function of temperature, and we have done a calculation yesterday that shows the difference between the probability of finding free electrons at certain energy level when you set the temperature at 300 Kelvin versus 950 Kelvin, right? And you've seen quite a huge increase in terms of the probability of occupation, which means density of free electrons will be increased as well. So it's a strong function of temperature, therefore. So for intrinsic semiconductor, when you talk about T equals to 300 Kelvin, we have a fixed value of Ni for silicon, for gallium arsenide, for germanium, and for some other intrinsic semiconductor material as well. But this is the commonly accepted values of Ni at 300 Kelvin. So for example, if you talk about silicon, then your Ni is either here means kita ada dua accepted values in the theory, right? In the theoretical part. So we normally accept the value of 1.5 times 10 to the 10 or 1 times 10 to the 10. So you can either use 1 times 10 to the 10 or 1.5 times 10 to the 10 per centimeter cube as the value of Ni for silicon at 300 Kelvin. So if you want to ease your calculation, definitely 1.0 is the easiest because you don't have to times or divide with 1.5, right? Doing with 1.0 is a lot easier because you just have to deal with the orders of magnitude. 10 to the 10, you just have to forget about 1 because it's just 1 anyway, right? So you can use either one. Okay, Fada, then what Ni equals N naught mean? Oh, okay. Ni and N naught means the very same thing. So Ni here means density of free electrons in intrinsic semiconductor, I for intrinsic, which is actually equal to N naught, or density of free electrons at thermal equilibrium condition in intrinsic semiconductor. So they are referring to the same thing, but you might need to use sometimes Ni, sometimes N naught to reflect different things. But actually they are looking at the same number, Ni and N naught. Okay. So we're going to see later on when you do the law of mass action and the calculation, you're going to see how does this Ni and N naught and P naught comes into the picture. Okay. So we're going to see later on. But essentially, they are referring to the very same number. If you have like, in this case, let me give you an example so that you can understand. If you're saying that your Ni here is 1.0 times 10 to the 10, sorry, 1.0 times 10 to the 10. So hold on, let me approve some other students joining. So if you're saying your silicon has an Ni of 1.0 times 10 to the 10 as written down here. So this 1 times 10 to the 10 is also equal to silicon N naught in intrinsic semiconductor. Okay, so Ni is more accurate if you want to refer to intrinsic, because when you talk about extrinsic later on, we're going to use N naught for thermal equilibrium condition as well, except it is in extrinsic semiconductor. Tapi kita tak tulis NEXT lah. You can do that to show that, but dia bukan satu convention lah, if like, right? But the moment you say Ni, you know that it's intrinsic. But N naught is more general in that sense because N naught can be used in intrinsic at thermal equilibrium, or it can also be used in extrinsic at thermal equilibrium. But the main point here for the naught is thermal equilibrium. Okay. So that's what it is. Later on, it's going to make more sense when you do the calculation because we're going to come back to N naught when we talk about extrinsic semiconductors. But it's no longer Ni because it's no longer intrinsic. So Ni in this case is very unique to intrinsic semiconductors. Okay, hope that explains. So for an electron hole pair to be created in an intrinsic semiconductor, a bond must be broken. So this is exactly what Patient says now. So you're going to have a free hole left in the valence band for every thermally excited electron you have in the conduction band. Because to be able to get that, you need to break a bond, right? Breaking a bond means creating electron hole pair where electron will be jumping to the CB and a hole will be left in the VB, right? By breaking a bond. A bond produces an electron hole pair. So more bonds means more electron hole pairs. And this requires energy. So that's why we have been discussing about moving, say, heating up your semiconductor from 0 Kelvin to, say, 300 Kelvin, at least to room temperature, then perhaps go up to 600 Kelvin. And you're going to see your thermally excited carriers increases due to the thermal energy supplied by the heat into the lattice, right? So that's why you induce excitation of valence band electrons from the VB to CB, okay, by thermal energy. So in this case, the energy is supplied by the thermal energy, giving thermal excitation, okay, to excite electrons into the CB. An electron in the VB must gain enough energy, right? Enough energy. So we've discussed the concept of band gap before. So if, let's just recap, if your band gap is 1.12, if you're supplying an energy of 0.8 electron volts, will you get any thermal excitation of electrons into the CB? No, right? Because minyak tak cukup. Right? We've discussed about the concept of traveling to mainland from mainland to island, crossing a bridge. Minyak tak cukup, it's not gonna, it's not even crossing the bridge. You won't go at all because the energy is not enough to begin with. So what if you're supplying a thermal energy of equal to 1.12? Will you get thermal excitation? Now you're supplying, right? So you're supplying 1.12 EV. The energy is just right. Chun-chun, yeah? Chun-chun is just right to overcome the energy gap, right? So then you're going to have your thermal excitation. So how about the third case? You are supplying a thermal energy of 1.5 EV. Will you get thermal excitation? Right. So you're going to get 1.5, you're going to supply 1.5, you're going to get thermal excitation. What happens to the extra energy supplied to the valence band electrons in this case? So it's going to go up further into the CB. It's going to go into the island further because minyak dia terlebih sikit. Right? You're supplying more. Then what happens next? You're supplying 1.5 more than enough to overcome the band gap. What happens next? What is the process that happens right after the excitation? Molar of T, we've discussed before. T, blah, blah, blah. Apa nama proses tu? What is the process name that happens right after the excitation? If you're supplying more than enough energy for the excitation to take place. Anyone? T.
Is it thermalization?
Yes, good. Very good. Voila. Thermalization process. Okay, thermalization. Thermalization. Huh? So where your excited electrons are going to drop to the conduction band edge. Band edge, huh? It's called thermalization process. Okay. So it's called thermalization, right? So since Ni represents the intrinsic carrier concentration, it also can also represent the number of bonds broken in an intrinsic semiconductor. So since Ni represents intrinsic carrier concentration, it also represents the number of bonds broken, because to be able to generate intrinsic carrier concentration that are free for conduction, you need to first break bonds, right? You need to first break a couple of bonds in order to get that. So that reflects the number of bonds broken, okay, indirectly. Right, let's have a look. Okay, you can see a graph now on the left where the y-axis is intrinsic carrier concentration, okay, from 10 to the 6, which is very, very low, up to 10 to the 19 as the maximum. And then you can see on the x-axis, the upper one, the upper scale is the temperature. Okay, upper scale is temperature, and then the x-axis below is 1,000 over temperature, or the inverse of temperature. Okay, the inverse of temperature in this case. So let's discuss this first question. Why more carriers at higher temperatures? So if you look at the graph here, if you go to if you increase the temperature, so if you increase temperature, you are looking at the right side or you're looking at the left side of the graph. When you increase the temperature, referring to the x-axis on the left, right? Because it's the inverse of temperature, 1,000 over T instead of T. Kalau T dia akan jadi macam tu lah. But now it's 1,000, it's inverse of temperature. That's why you're expecting, if you go to the left, you're actually increasing the temperature, and then you're going to get more or higher intrinsic carrier density Ni. So then the question is why you get more carriers at higher temperatures, right? That more excitation, more thermal energy supplied to the system or to the lattice, exactly like what we've discussed in the previous page. Okay, so this is the energy supplied by going to higher temperatures. So you're going to get more thermal excitation. So you're going to get more and more electrons jumping into the CB and ready for conduction. And that's why you are getting like that and like that and like that for germanium, silicon, and gallium arsenide in this case, right? So you're going to see if you run your temperature, say around here, your silicon intrinsic carrier density is about, you look at silicon now, the middle curve. So that's about 10 to the 12, right? So that's about close to half of 10 to the 12. And then when you increase the temperature to say around 500 degrees C in this case, so you're going to get somewhere there. You're going to get about 17. Okay, so that's like 5 orders of magnitude increase by increasing the temperature from 100 degrees Celsius to 500 degrees Celsius due to thermal excitation. Okay, so more electrons from BB gain enough energy to jump across the band gap to get to the CB and ready for conduction. Okay, so this, remember, this has nothing to do with doping yet. This is just by manipulating the temperature of your semiconductor material without even bother about the doping yet. Okay, this is purely intrinsic. Now we are moving into extrinsic. So what do you see on this picture? Why do I call it extrinsic? What do you think? Jangan terbayang air pula. Kau rasa? Yes, it's impurities, right? Impurities. Just to show impurities in the water, exactly, impurities. So, nampak macam ni pula, cincau pula. Hitam-hitam. Right. So it's impurities, referring to impurities. Good. And in this case, when you talk about extrinsic, we are talking about incorporating impurities into the lattice. Okay, impurities. But when you include these impurities, in this case, if you recall what we learned in the very first lecture about semiconductor material, in this case, we are incorporating the impurities that we call desired impurities. So in the first class, we have divided impurities into desired impurities, or what we also call as dopants, because you want to incorporate by design, you want to control the amount of dopants. And on the other hand, you may also have undesired impurities like metal contaminations, something that you don't want to be in your semiconductor material, but they are there due to some incidents or, cross-contamination in the equipment or handling or whatnot. So those are undesired impurities. But when you talk about dopants, you want to control the incorporation of dopants into the lattice, and therefore they are called desired impurities. Okay, macam you purposely include these impurities for you to drink. Okay, so those are the impurities. Right. So what are extrinsic semiconductors? Okay, what are extrinsic semiconductors? So an extrinsic semiconductor can be defined as a semiconductor into which impurity or dopant, impurity or dopant has been introduced or incorporated, giving it different electrical properties than the intrinsic semiconductor. So remember last time we talked about a doping briefly as a process or as a mechanism to alter, to change the semiconductor, the electrical properties of your semiconductor materials by certain level, right? So you can actually control this process by incorporating a certain level or certain type of impurities into the silicon lattice in this case. It can also be germanium, it can also be gallium arsenide, it can also be other semiconductor materials, can be ternary, can be quaternary. Cumanya kita, for this particular course, we keep referring to silicon as our reference, but it is also applicable to some other semiconductor materials, except the dopants the dopant materials are different depending on which is your host atom. Okay, if you're talking about zinc oxide, then you're talking about aluminium to make it N-type. Tapi untuk silicon, if you use aluminium, it's going to get P-type, right? So that means the dopant is doing different job in different host atoms, just like the difference of using zinc oxide and silicon as the host with respect to aluminium as the dopant. So it's gonna give you opposite polarity. Okay. So when I say silicon here, then I'm always referring to group 3 for p-type, group 5 for n-type. Okay. But if you talk about some other semiconductors, then you have to really be careful on the type of materials that you use as your dopant. So for impure or extrinsic semiconductors, your N is no longer equal to P. Okay, so remember last time, just now I mentioned about in intrinsic, we have discussed about this. Father asked about this now. Ni equals to N naught equals to P naught in intrinsic. But in extrinsic, N is no longer equal to P because you are incorporating specific dopants into the lattice in order to alter the conductivity of your semiconductor material. Either you want to make it more N-type or more P-type. More N-type or more P-type simply means that N is no longer equal to P, right? Because it's going to get skewed to one side. It's more positive or more negative. So in fact, small amounts of impurities can radically change the electrical properties of the semiconductor material. So you don't have to have a very big amount of impurities incorporated, because a very small amount can already alter the electrical properties of semiconductor a lot. So group 5 element like phosphorus, arsenic, antimony have 5 valence electrons. And if it's bonded to silicon, silicon has 4 valence electrons, and you're going to have more, you're going to have 1 free electrons wandering through the lattice unbonded because it's not bonded, right? So the 5th one is easily ionized. So it's wandering around and getting ionized easily because it only requires about 0.02 eV of energy from the lattice in order to get fully ionized. Okay, and this process is called ionization. For you to get the electron or the hole to alter the conductivity, they have to be ionized. Okay, maksudnya kalau you incorporate phosphorus or arsenic or antimony ataupun group 3, but they are not ionized in the lattice, they will just stay in the lattice doing nothing. Maksudnya you may have phosphorus incorporated, but then you don't see any change in electrical properties when you do the measurement, simply because there's no ionization takes place. And to be able to get the ionization, you need to apply this amount of energy, at least 0.02 eV for the dopants to be ionized. Okay. Kalau tidak, if you get the dopants to be in the lattice, incorporated through doping process, but if they are not ionized, they will turn, or they will end up as defects. Because you incorporated something new to the lattice, okay, you may affect the lattice condition to some extent, and then they will end up as defects. And yet they don't contribute to any electrical properties at all. I mean, you aim to alter conductivities, but then they don't really alter the conductivity because they're not ionized. And they even kill your devices later on because they are defects. So we're going to learn later on, when you talk about defects, you're going to see in a process that we're going to learn in, I think, week 5 perhaps, when you have conduction band and valence band. The moment you have these defects are something physical. You can see under the microscope if they are big enough, or if they are too small, you may have to go under SEM or perhaps worst case DM to be able to view the defects. So they are physical thing on the semiconductor material or inside semiconductor material. But electronically, tadi dia physical, but electronically they appear as a state in your band gap, right? So defects are physical, you can see to some extent depending on the size, of course, but electronically they appear as a trap state in the band gap. So they will suck or kill or remove your free carriers later on. So we're going to see this one in a process that we call recombination. Okay, So we're going to come back to that. So group 3 element on the other hand, so let me go through for another 5 minutes perhaps. Group 3 elements on the other hand, like boron, aluminum, gallium, have 3 valence electrons, and if they're bonded to silicon, so there's 1 lack of electron. So a fourth electron is easily accepted because it's vacancy from silicon lattice, leaving behind a positively charged hole, right? So the moment you incorporated group 3, you're going to introduce holes, right, in the lattice. And again, the required energy is very small, 0.02 eV of energy from the lattice for the ionization to take place. If they are not ionized, they will appear as defects and they even kill the devices later on. So doped silicon, let me just go through this concept of doped silicon, then we're going to stop. Let me just introduce doped silicon for a bit. Right, doped silicon means silicon is doped, or dopants are incorporated into silicon, whether it's p-type or n-type, group 3, group 5. Because the ionization energy from group 4, group 3, and 5 is so small, so which is around 0.02 eV, so nearly 100% of these atoms are ionized at room temperature. So we assume that due to the small energy required, 0.02 eV, nearly all the incorporated dopants are ionized at room temperature. Okay, maksudnya kita assume they are electrically activated. So when you say they are ionized, they are electrically activated. In other words, some references use this word, electrically activated. Maksudnya you incorporate them into the lattice and you wake them up. You energize them electrically. Maknanya you kejut dia, but you bagi some energy for them to be electrically active. Kalau they tak ionized means they are not electrically active or they are electrically inactive. So that's why they are defects. So group 5 and 3 elements are intentionally added intentionally. So that's why we mentioned about desired impurities. You want to control, you want to incorporate, you know the level you want to introduce to the lattice. To change its free electrons and holes, which essentially means N is no longer than P eventually, the moment they are electrically activated. So this is the most important feature to form a PN junction later on. So to be able to get a PN junction, remember last time, I think in the past few lectures, I mentioned about the typical doping level in a solar cell, a typical doping level in IC. IC is more complicated because of many layers, but solar cells, you are pairing, for example, p-type 10 to the 16 with n-type 10 to the 19. So this is where the doping comes in, right? This is where the control of your dopants comes in. Either you want to dope at 10, 17 or 18 or 19 or keep it at 15 or 14, depending on the requirement of your final devices, okay? So this will be very, very important when you talk about PN junction. And this has to be understood first before you combine P and N, because now we are only talking about making P or making N, and then later into the weeks we're going to talk about combining P and N and what happens next, right? So combining P and N means we're talking about regions of semiconductor that are doped with P-type in combination with N-type. So sekarang we're just talking about either this piece P or either the top piece N. Next, we're going to talk about combining this P and N, or it can also be P on N. It can also be different combination like this. Nanti kita akan tengok dalam PN junction. It can also be P and but you put intrinsic in the middle, pin, P-I-N. Boleh juga macam tu. It can also be like NIP, NIP. Right? It can be the common convention for you to design a PN junction is either P on N, N on P, or it can either be pin or nip. Okay, so this is where you include a thin layer of intrinsic semiconductor in between for certain task in the device. Okay, so that's why you have to understand intrinsic, extrinsic, doping level. Barulah we can discuss the junction and stuff and the devices. So N0 and P0 are the densities of thermally, N0 and P0 are the density of thermally generated free electron and hole respectively at 1 times 10 to the 10 in silicon at 300 Kelvin. If you are talking about intrinsic silicon, okay, Ni, which is essentially Ni equals to N0 and P0. But when you talk about dope, ayat ni actually is meant for intrinsic. I'm referring to intrinsic because we're talking about this value 1 times 10 to the 10, or it can also be used as 1.5 times 10 to the 10. Either one is fine, but obviously 1 is easier. But when you talk about dope silicon, the level is no longer the same. We're gonna look into the next 2 slide perhaps. Right, in dope silicon, tadi in intrinsic kita pakai Ni. So in dope silicon, we're gonna change the parameter. Instead of Ni, we're gonna use Nd or Na, right? Ni for intrinsic, Nd will be for donor concentration. Donor means it's meant for N-type because N-type will be donating free electrons. The other 5 bonded to silicon 4, they're going to have free electrons from group 5, and therefore we call group 5 as Nd, ataupun silicon doped with N-type as Nd, because D stands for donor. A here stands for acceptor, which is meant for group 3. So if you're doping your silicon to make it more P-type, you're going to refer to Na instead of Ni, right? So both are the density of dopant present in the silicon, which refers to donor atoms for Nd, for N-type, acceptor atoms, Na for P-type, respectively, typically more than 1015, okay? To be able to say that the silicon or the semiconductor is effectively doped, even though you can also say that it's 1014 can also be considered, but typically for it to see to show up as the doping effect, you'll typically see at 15 and above, right? So in N-type silicon, when you dope with phosphorus, antimony, or arsenic, in this case, I would like to compare with Ni that we just discussed in the previous slide. Nd is way bigger than Ni. Nd is way bigger than Ni. So remember, Ni is 10 to the 10. So your Nd, if you assume your Nd is, say, 10 to the 16, for example, 10 to the 16 per centimeter cube. Now, 10 to the 16 is way bigger than 10 to the 10. And therefore, the effective carrier density that you have in the N-type is approximately equal to Nd, because 10 to the 16 is way bigger than 10 to the 10, and 10 to the 10 becomes so negligible, and your effective carrier concentration, effective electron concentration to be more accurate, because it's N-type, is now equal to Nd. You can then equate N equals to Nd in doped silicon, okay? So on the other hand, if you talk about P-type silicon, where your Na is way bigger than your Ni, so let's assume 16. So now 10 to the 16 is way bigger than 10 to the 10. 10 to the 10 will become very negligible in that condition, and therefore your effective hole concentration is now approximately equal to Na, or you can say that P now equals to Na, right? So in N-type, N equals to Nd. In P-type, P equals to Na. In intrinsic, previously, Ni equals to N0 and P0, or is equal to 10 to the 10. N0 and P0 tak masuk dalam this comparison yet because they are referring to thermal equilibrium anyway. And you're going to see N0 and P0 for both N-type and P-type as well, okay, later on. So in device fabrication, we're going to learn later on, 1015 to 17 is usually called lightly doped, usually, but there's no specific border. If like some are referring to 14 to 16 as lightly doped, some are referring to 15 to 17. But above 18 and above, it is usually called heavily doped. Okay, there's no strict border between lightly and heavily, moderately. There's no light, because kadang-kadang ada, some are using 15 as still lightly doped. On the other references, you'll probably see a bit, different terminology being used for this particular range. So, but in essence, you can say that if it's lightly doped, then you can say it's between this region. But heavily doped is typically referring to 18 and above. Okay. So let's just stop here. I'll continue tomorrow with from this to the next one. Okay, you're gonna come back to this band diagram, density of states, Fermi Dirac distribution function, and then the effective carrier concentration that we use in the previous topic that we learned. Previous topic to discuss about dope semiconductors or dope silicon. Okay. So any questions so far on extrinsic semiconductors versus intrinsic semiconductors? Can you guys follow so far? Okay, tak ada soalan? Semua paham? Right, good. There's no question then. Yeah, so far okay. Right, all right. So I'll see you then tomorrow, 10 a.m. Right? Bye-bye. Take care. Assalamualaikum.